Good afternoon. Welcome to today's lecture on the relationship between energy and mass. Now, this might sound like kind of a weird topic, but we're about to get into probably one of the last big revelations of this course and one of the really big revelations of the last century or so, a little more than a century in physics. Now, according to the reference tables, if you look at the front of the reference tables, it will tell you that the mass of a proton and a neutron is the same, 1.67 times 10 to the negative 27th kilograms. And the mass of an electron is 9.11 times 10 to the negative 31st kilograms. These are familiar numbers to us. We've used these before. The one thing that kind of is weird about these numbers is you don't get a sense of how small they are. That's negative 31st, by the way. You don't get a sense of how small they are just because, or what the sizes are, just because they're so small. It's kind of tedious, and we don't get a lot out of writing the scientific notation every time. So what has happened is scientists have come up with a unit called the universal mass unit to describe really small masses like this. Now, there is a conversion for this on the front of the reference tables, but you are not ready for that yet, okay? I'm going to give you a conversion that's not on the front, and eventually we'll see why the conversion on the front is the way it is. One universal mass unit is 1.66 times 10 to the negative 27th kilograms. So very similar to the mass of a proton or a neutron. The way they got this number is it's actually 1/12 of the mass of an atom of carbon. Why did they choose carbon? I have no idea. Why is it 1/12? I don't know. That's just that's how it was based off of. If we were to convert the masses of protons, neutrons, and electrons into universal mass units, here's what we would get. I could do the math, but I'm just going to hope that you trust me on this math here. The proton mass is 1.0073 universal mass units. The neutron mass is actually very slightly heavier, 1.0087 universal mass units, and an electron is still tiny, 0.0005 U. So we see that proton and neutron masses are actually not quite the same. They're very slightly different. Electron mass is still much lower. We can actually use these masses to discover something very interesting about mass and energy. Here's what we're going to do. Let's consider an alpha particle. An alpha particle is just a really fancy name for a nucleus of a helium atom, a helium nucleus. If it's a helium nucleus, that means that it consists of 2 protons and 2 neutrons. So we should be able to very easily figure out what the mass of the helium nucleus is by adding together the masses of the 2 protons that make it up and the 2 neutrons. So the total mass would be 2 times the mass of 1 proton plus 2 times the mass of a neutron. Since there's 2 protons, 2 neutrons, plus 2 times 1.0087, I get 4.032 U for the mass of the individual parts of a helium nucleus. Makes sense. So individually, the mass of 2 protons plus 2 neutrons comes out to be this. So you would expect that the mass of the helium nucleus is the same. And that's where you'd be wrong. Turns out that when you have an actual helium atom, and we're discounting the mass of the electrons here, the mass of the actual helium nucleus, once it's all combined, is only 4.0015 U. This is not a mistake. It's not an error in the lab. Okay, there's no wrong procedure here. It's not that we're forgetting to account for anything. The mass is literally different. This is crazy, okay? A lot of stuff in modern physics is just nuts. It's absolutely insane. But it seems that the mass of these individual protons and neutrons, when you add up the mass of them individually, it's greater than the mass when they are all together. There's a mass defect. There's a difference in these masses of, so let's see, 4.032 minus 4.0015. There's a difference of 0.0305 U. How is this possible? Let me give you a scenario. This is like saying that if I took 5 of these 1 kilogram masses right here, and I just tied them together with very, very light string, then the effective mass of them all together would only be like 4.5 kilograms. Okay? That's crazy. That doesn't seem like it should make sense. That's nuts. It seems like, it should be 5 kilograms, but that's not how this works. Okay? Here's the reasoning. It turns out that this missing mass is used as what's called binding energy. In order to keep the protons and neutrons together, so this has something to do with a strong force as well, and I'm not super well versed in it, but in order to keep these together, it actually requires some energy. And the only place that these protons and neutrons can get energy is if they lose a little bit of mass. That little bit of mass gets turned into energy, and then it leaves. It kind of leaves these frozen together. So a little bit of mass actually leaves. And the mechanics of that aren't really what I need you to focus on. The more important idea is that literally some mass, if you're going to bind these together, some mass from those particles is given up and is created, or not created, but it is changed into energy. Literally, some mass is taken and it is changed into energy. That is wild, okay? We have always talked about mass is mass, it's matter, it's how much stuff is in an object. Energy is this thing, this kind of ambiguous thing that allows systems to move. We are now seeing that you can take mass and directly convert it into energy, because it turns out that mass and energy are really just two different forms of the same thing. Matter of fact, scientists who study this sort of thing, they don't even refer to them separately. They literally refer to the combined pair as mass-energy, mass energy. We don't talk about conservation of mass or conservation of energy when we're dealing with things like this. We talk about the conservation of mass energy. They are the same thing, just in two different forms. So, and I do want to make the point before we flip over to the back, how would you get these particles separated? Well, some energy comes in, and basically that breaks the bonds between them, and it also restores some of the mass, so that when they're separated, they gain their masses back. Again, the key thing is that mass and energy can be converted from one to the other, and I think that's pretty wild. This is not a new thing. One of the reasons that Albert Einstein is famous is because he studied this and he actually came up with the equation for calculating how much energy is stored in a certain amount of mass. In other words, if you take some mass and you said, okay, I want to get energy out of this, I want to change this mass directly into energy, Einstein provided the equation for doing that. And that equation, very famously, is E equals mc squared. This equation shows us that the mass of an object can be changed into a certain amount of energy. Okay? I'm not going to get into how you change it into energy, but mass has an equivalent amount of energy. Okay? A certain amount of mass has an equivalent amount of energy. If we could take that mass and change it into energy, that's what we're talking about here. You simply multiply by the speed of light squared. The rules for using this equation are that the mass must be in kilograms. The energy must be in joules. If you don't have those units, this equation will not work. And just a note of caution, the speed of light is squared. Please don't forget that. That's the biggest mistake people make with this. All right. Let's get to some examples, okay? We're already in crazy town kind of with this new idea that mass can be converted directly into energy. Let's see how much energy we can get out of some mass. How much energy is stored in 1 kilogram of matter? Well, the equation is E equals mc squared. Mass must be in kilograms, so I'm good there. 1 kilogram. Speed of light is 3 times 10 to the 8th meters per second. When that gets squared, 3 times 10 to the 8th squared is 9 times 10 to the 16th times 1. The energy content of 1 kilogram of mass is 9 times 10 to the 16th joules. Now, you probably don't have too good a read on how much energy that is. It seems like a lot, but really, how much is it? I want to talk about volcanic explosions for a second. Completely switching topics. You've heard of some, probably like Mount St. Helens about 40 years ago in Washington, or Vesuvius that destroyed the town of Pompeii in about AD 79. Those were not the biggest recorded volcanic eruptions. I believe the biggest was an Indonesian volcano called Krakatoa. I think it exploded in 1881. It erupted in 1881. This explosion was so violent and so loud and released so much energy that the sound from this explosion, from this eruption, was heard in Australia. Now, I don't know how good you are with your geometry. Indonesia is like kind of over by Australia, but it's still separated from it by like over 1,000 miles at least. We're talking about such a powerful eruption that the sound was heard over 1,000 miles away, probably more than 1,000 miles away. The amount of energy that was present in that eruption is about the same scale as this. This is about as much energy as the Krakatoa eruption, which is the most violent volcanic eruption in recorded history. Think about how crazy that is. 1 kilogram. This is a kilogram. If I could take all this mass and convert it directly into energy, it would be the same amount of energy as the biggest explosion we have ever recorded. That seems like it's not true, but it is. This equation derives from experiment that has been proven time and time and time again. Now, thankfully, we don't have great ways to simply convert mass into energy. There are ways to do it, but this is not just going to randomly pop into energy, okay? It's pretty stable as mass. But if we were able to take this much mass and convert it to energy, we would have a ton of energy. Think about how that could like power like a good chunk of the world for like a good amount of time. As a matter of fact, the next example, in 2008, the world used approximately 5.2 times 10 to the 20th joules of energy. What is the equivalent of this much energy in mass? E equals mc squared. 5.2 times 10 to the 20th joules equals mass. And by the way, since we know that the speed of light squared, I know that 3 times 10 to the 8th is 9 times 10 to the 16th. You still have to write 3 times 10 to the 8th meters per second squared. You cannot just simply substitute in 9 times 10 to the 16th, even though you know it's going to be that. 5.2 times 10 to the 20th divided by 3 times 10 to the 8th squared gives us a mass of 5,778 kilograms. If you could take this much mass and convert it directly into energy, it could have powered the world for 1 year in 2008. I did some research. 5,778 kilograms, that's a lot of mass, but that is less than the mass of 1 grown elephant. Okay? Less than the mass of 1 grown elephant. If you turn that much mass into energy, could power the world for 1 year. That, again, is crazy. Take an adult male elephant. Those are big things, but in the grand scheme of things, compared to the rest of the world, that's not a ton of mass. Okay? Take 1 grown elephant, convert all of its mass into energy, and we would have enough to power the world for an entire year, with some left over. That is just so bonkers to me that it's so hard to conceptualize. But again, this equation has been proven time and time again in experiment. I want to switch gears here a little bit and go back to talking about universal mass units, because a lot of times, it's very hard. We can't just take this 1 kilogram and convert it straight to mass. That's not how convert it straight to energy. That's not how it works. Instead, what usually happens is in that example where the helium nuclei was forming based on the individual protons and neutrons, there was we saw that there was a mass defect. Some of the mass was given up, and the mass decreased because some of that mass turned into energy. So what we usually see as the application for E equals mc squared is small amounts of mass turning into energy, such as during fusion or fission. So we want to talk how much energy is stored in 1 universal mass unit. Well, in order to do this right now, this equation only works if I have the mass in kilograms and the energy in joules. So the very first thing I need to do, I have mass in universal mass units right now. I would have to convert the mass to kilograms. I'd have to plug into the formula. And then I'd have to convert that energy that I get into electron volts. Okay, I guess I don't have to convert into electron volts, but that's where we're going to go with this. So let's do that first. Let's do 1U. We're going to convert that. We know the conversion from the front is 1U equals 1.66 times 10 to the negative 27th kilograms. So very clearly, this is 1.66. I guess I probably didn't need to do that, times 10 to the 27th kilograms. Let's plug that in here. mc squared, the energy equals 1.66 times 10 to the negative 27th kilograms times 3 times 10 to the 8th meters per second squared. The energy comes out to be a very small number. 1.494 times 10 to the negative 10th joules. And that's why I want to convert to electron volts. This is a tiny amount of energy. Let's convert this to electron volts. Let's see how many electron volts it is. Remember, an electron volt is just a very small unit of energy. The conversion is on the front of the reference tables. 1.6 times 10 to the negative 19th joules is 1 electron volt. So I'm going to end up dividing this by 1.6 times 10 to the negative 19th. And I end up with, let's see, 3, 6, 7, 8. I end up with 9.3. And so I should have rounded this a little bit. This number is not exact, so this number is going to be a little bit not exact as well. I'm going to go with the actual number. 9.31 times 10 to the 8th electron volts of energy are stored in one universal mass unit. That's a lot of electron volts, not a lot of joules. You got to work with me for a second on this one. So this problem shows us there's a conversion on the reference tables for universal mass units. It doesn't convert into kilograms. It converts into a type of energy. If I have 9.31 times 10 to the 8th electron volts, I could rewrite this in an incorrect form, meaning the form is just not how we normally write it, as 931 times 10 to the 6th electron volts. If I'm making this number bigger, I got to make this number smaller to compensate. I move the decimal twice, which means this number goes down by 2, becomes 6. 931 times 10 to the 6th. If you don't believe me, try it. Now, I look at the reference table, and I see that on the table that we looked at, like the very first day, 10 to the 6th is this, has the symbol mega. So I could replace this as 931 mega electron volts. Matter of fact, if I wanted to put this back into scientific notation, I could write 9.31 times 10 to the 2nd mega electron volts. And that is actually the way that this is listed on the reference tables. One universal mass unit equals 9.31 times 10 to the 2nd mega electron volts. That's a useful conversion to know if you're dealing with mass being converted to energy. Oh, I wrote it wrong. That's a useful conversion to know if you're dealing with mass being converted into energy and you're dealing with very, very small masses, like fractions of a proton or a neutron that gets lost when protons and neutrons bind together. Some of that mass defect that arises because those two particles are binding together, we can figure out how much energy is stored in that. So let me give you an example. Let's do the example that we had before. When helium is created from 2 protons and 2 neutrons, you take 2 protons, bring them together, take 2 neutrons, bring them together, it has a nuclear mass of 4.0015 U. But the individual masses of all those different things was 4.032 U. You can check that on the front. How much energy is released when helium forms? Well, let's recall that the mass difference between the sum of the product, the sum of the what goes into the helium nucleus, and then what the mass of the actual helium nucleus was 0.0305 U. Let's convert that into energy. 1 U is 9.31 times 10 to the 2nd MeV. So we're going to do 0.0305 times, I'm going to do 9.31 E2. And what I get out is 28.4, I'm going to round, MeV. Now, I don't think in MeVs. I think in electron volts and joules. So I could convert and figure out the mass in, or figure out the energy in electron volts and joules. That's exactly what I'm going to do. So I know that 1 MeV is 10 to the 6th EV. So I'm going to change this to, so let's see, times 10 to the 6th. So this becomes, let's see, 3, 6, 7, 8. Did I do that right? No, I didn't. I'm sorry. 28.4 times, let's see, 1 times 10 to the 6th. There we go. Yes. 2.84 times 10 to the 7th electron volts. I could even convert that into joules. (4.54) times 10 to the negative 12th joules. All of these are the amounts of energy that are released when a helium nucleus comes together. A helium nucleus comes together during nuclear fusion. When you take two hydrogen nuclei, smash them together to get helium, this much energy is released every time. Okay, these are all equivalent amounts of energy. And this is a small amount of energy. But think about this. This exact reaction happens in the sun at least 10 to the 20th times per second. Multiply this by 10 to the 20th. Okay, at the very least, times 10 to the 20th. You're getting a huge amount of energy out. Absolutely enormous. And it's probably many more times than that. I was just spitballing with a number. But this reaction that produces this much energy happens in absolutely insane, an almost unimaginable number of times per second in the sun. So all of those add up, and we end up with the sun being this huge producer of energy. Okay? Because of this little tiny mass defect, the amount of mass given up by these protons and neutrons to bond together, that mass gets turned into energy, and that energy powers everything in our life, everything on Earth. Okay? All comes from the sun that's using the energy from this bonding. The mass gets turned into energy. Key things to take away. Mass can be turned into energy. Energy can be turned into mass. If you have mass in kilograms and want energy in joules or vice versa, you use Einstein's famous equation, E equals mc squared. If instead you have the mass in universal mass units or the energy in electron volts or mega electron volts, then you simply use this conversion right here. Okay? You don't want to, I mean, think about it. If we could have done this problem down here that we just did right at the end, we could have done this problem by converting this much mass into kilograms and then plugging into here and then solving for the energy and converting it back. But instead, we just used a conversion and we just wrote it a few different ways. Okay? So you have two different ways to convert from mass to energy. One using just, one using E equals mc squared and one using a conversion. Okay? Biggest takeaway though, mass and energy are really the same thing, just in different forms. Our last video will be on what is known as the standard model of particle physics, our best theory about how the universe is structured and everything that makes it up.